are going to discuss charge distribution. So in previous video, we are going to already discuss in charge distributions. So charge distributions are two types. One is non-continuous charge distribution. Second one is continuous charge distribution. So what is non-continuous charge distribution? A charge is distributed non-uniformly, so that is called the non-continuous charge distribution. So a charge is distributed continuously, so that is called the continuous charge distribution. So next one, so continuous charge distribution. Continuous charge distribution. So what is continuous charge distribution? A charge is distributed continuously, so that is called the continuous charge distribution. So now, so continuous charge distributions are three types. So there are three types. So first one is so linear charge distribution. So this is the first one. So linear charge distribution. So second one is surface charge distribution. Surface charge distribution. So third one, so volume charge distribution. So volume charge distribution. So there are three types of distributions. So one is linear charge distribution, surface charge distribution, volume charge distribution. So linear charge distribution having linear charge density. So linear charge density. So it is denoted by lambda. So next is surface charge distribution. So having surface charge density. So it is denoted by sigma. So third one, so volume charge distribution having so volume charge density. So volume charge density. It is denoted by rho. So here linear charge distribution having linear charge density. So surface charge distribution having surface charge density. It is denoted by sigma. Volume charge distribution having volume charge density. So that is denoted by rho. So these three questions are very, very important for one-mark questions. Keep on your mind, don't forget. So linear charge density, it is denoted by lambda. So surface charge density, it is denoted by sigma. Volume charge density, it is denoted by rho. Okay. So there are three types of continuous charge distribution. So what is continuous charge distribution? A charge is continuously. A charge is distributed continuously. That is called the continuous charge distribution. Continuous charge distribution. So this is the continuous charge distribution. So now we shall discuss one by one. So first of all, so linear charge density. So it is denoted by the symbol is lambda. So linear charge density. So then first one. So linear charge density. So linear charge density. So it is denoted by lambda. So what is the definition for linear charge density? So charge per unit length. So charge per unit length. So charge per unit length. So this is called the linear charge density. So lambda is equal to charge divided by length. Charge divided by length. So this is lambda. Okay. So linear charge density. So that is equal to lambda is equal to charge by length. So charge per unit length. So that is called the linear charge density. So what is the SI unit? So charge SI unit is Coulomb, length measured in 1 by meter. So meter inverse. Coulomb meter inverse, not centimeter inverse. Okay. So don't confuse. Coulomb meter inverse, not centimeter inverse. Okay. So the SI unit of linear charge density is Coulomb meter inverse. So what are the examples? So examples. So for example, if you take the wire, so this is the wire. a charge is distributed continuously. So this is the positive charge. So here, so L is the length of the wire. So here charge is Q. Okay. So what is the linear charge density? Lambda is equal to charge divided by length. So this is the formula for linear charge density. Charge per unit length of the wire. So that is called the linear charge density. So another example is if we take the ring. So this is the ring. So when a charge is distributed continuously like this. So this is the another example for the linear charge distribution. So ring. So this is wire. So this is wire. Okay. So next one. So what is the second one? So surface charge density. Surface charge density. So it is denoted by sigma. Surface charge density is denoted by sigma. So what is the definition for surface charge density? Charge per unit area of the conductor or charge per unit area. So that is called the surface charge density. So charge per unit area. So charge per unit area, so that is called the surface charge density. So it is denoted by the symbol sigma. So sigma is equal to charge divided by area. So charge by area. So this is called the surface charge density. So what is the SI unit? So SI unit is so charge measured in coulomb. So area measured in meter minus. So that means 1 by meter square. So in can be written as coulomb meter units, not centimeter minus 2. Okay, coulomb meter minus 2. So this is the SI unit of surface charge density. So what are examples? Example. So now if we take the metal plate, so this is the metal plate. When a charge is distributed continuously, so like this, charge. So this is charge Q. So area of the plate is A. So Q is the charge distributed. A is the area of the metal plate. So this is metal plate. So what is the formula for surface charge density? So surface charge density sigma is equal to Q by A. So this is the formula for surface charge density. Sigma is equal to Q by A. So another example for conducting metal sphere. So this is a metal sphere. So when a charge is continuously distributed, so this is metal sphere. So these are the examples for the surface charge density. So next one, so volume charge density. So next one, volume charge density. So it is denoted by the symbol is rho. So volume charge density. So next third one is volume charge density. So third one, volume charge density. So it is denoted by rho. So rho is called the volume charge density. So what is the definition for volume charge density? Charge per unit one. Charge per unit volume. So this is called the volume charge density. So charge per unit length, so that is called linear charge density. Charge per unit area, so that is called surface charge density. Charge per unit volume, so that is called the volume charge density. So it is denoted by the symbol is rho. So rho is equal to charge divided by volume. So this is the formula for volume charge density. So rho is equal to charge divided by volume. So SI unit. So charge measured in coulomb. So volume measured in meter cube. So coulomb meter minus 3, not centimeter minus 3. So this is coulomb meter minus 3. So this is the SI unit of volume charge density. So what is the definition for volume charge density? Charge divided by volume. So next example. So now if we take the example, non-conducting sphere. So non-conducting sphere. So this is the example for the volume charge density. So here if we take this sphere, so like this. So when a charge is distributed continuously, this is the example for the volume charge distribution. So here charge is Q. So volume of the sphere is V. Therefore, so density rho is equal to charge divided by volume. So this is the volume charge density. So rho is equal to Q by V. So charge per unit volume. So this is the volume charge density. So these three are very, very important. So linear charge density, surface charge density, okay, volume charge density. Okay. So next one. So we know that. So in previous video we are going to discuss Gauss law. So once remember the Gauss law. So what is the statement of Gauss law? The total electric flux. The total electric flux passing through any closed surface. The total electric flux passing through any closed surface. So closed surface is three-dimensional surface. The total electric flux passing through any closed surface, that is 3D surface, enclosing a charge, is equal to 1 by epsilon naught times the magnitude of the charge enclosed. So that is the statement of the Gauss law. So mathematically, closed integral E bar dot ds bar is equal to, so Q inside divided by epsilon naught. This is the statement of the Gauss law. So this is the mathematical of Gauss law. So closed integral E bar dot ds is equal to Q inside divided by epsilon naught. So next one. So Gauss law is always applicable but not always useful. So Gauss law is always applicable but not always useful. So now applying the Gauss law but any charged body. So that means linear charged body, surface charged body, volume charged body. So now one body ಒಂದು ಚಾರ್ಜಿಂಗ್ ಬಾಡಿಗೆ ಗಾಸ್ ಅಪ್ಲೈ ಮಾಡಬೇಕಂದ್ರೆ ಕಂಪಲ್ಸರಿ we can draw the Gaussian surface. So we can draw the Gaussian surface. Without Gaussian surface does not explain the Gauss's law. So now we apply the Gauss's law. Must we can draw the Gaussian surface around the charge distribution of the body. So this point is very, very important. Keep on your mind. So now apply the Gauss's law. We must and should be draw the Gaussian surface around the charge distribution. Okay. So what is the definition for Gaussian surface? So we can draw an imaginary closed surface around the charge distribution of the body. So that is called the Gaussian surface. So Gaussian surface is the imaginary surface. So we can draw around the closed surface of the charged body. So that is called the Gaussian surface. So without Gaussian surface does not explain the Gauss's law. Okay. So this point is very, very important. So for example, so what is Gaussian surface? So Gaussian surface. So we can draw an imaginary closed surface around the charge distribution of the body. So this surface is known as the Gaussian surface. So for example, now if we take the wire, so this is the wire. So this is wire. So in this wire we can apply the Gauss's law. So does not apply directly. So Gauss law does not apply directly. We can draw the imaginary surface around this charge distribution. So now we can draw the Gaussian surface like this. So this is the cylindrical Gaussian surface. Okay, so this is the cylindrical Gaussian surface. Okay, so we must not draw the on the Gaussian surface from other. Okay, so we can draw an imaginary closed surface around the charge distribution that is called the Gaussian surface. So here infinity, so straight wide infinity uniformly charged wide. So now applying the Gauss's law, you can draw the imaginary Gaussian surface. So now if you take the plate, so this is the metal plate. So this is metal plate. So having the positive charge like this. So now we are applying the Gauss's law. First of all, we can draw an imaginary Gaussian surface. So like this. So this is the imaginary Gaussian surface. So this is cylindrical Gaussian surface. Okay. So first of all, we are applying the Gauss's law means we can draw the Gaussian surface. So without Gaussian surface does not explain the Gauss's. Okay. First of all, we must draw an imaginary closed surface around this charge distribution. So that surface is known as the Gaussian surface. Without Gaussian surface does not apply the Gaussian. Okay. So this is very, very important. So first of all, we can draw the Gaussian surface. Okay. So next one. Next one. Gaussian surface is symmetrical charge distribution. So Gaussian surface is symmetrical charge distribution. So Gaussian surface is symmetrically charge distribution. So next third point. Electric field must be symmetric. Electric field must be symmetric. That means same, constant, or equal at every point. At every point on the Gaussian surface. At every point on the Gaussian surface. Okay, this is thought. So electric field must be symmetric or same. So same idea of the constant or equal. So symmetric and the same idea is electric field is symmetric. Electric field is constant at every point. Electric field is equal at every point on the Gaussian surface. So next one, the angle. So the angle here. So that angle here. So is the angle between A bar and area. So third one, the theta. So that means angle between E bar and A bar. E bar and A bar is same at all points. Same at all points. That means theta is equal to 0 degree or 90. So the angle between E bar and area. So is equal to theta equal to 0 degree. Another theta equal to 90 degree. So these are the applying the Gauss's. So first of all, we can draw the imaginary closed surface around the charge distribution of the body. So that is called the Gaussian surface. In this Gaussian surface, electric field must be symmetrically charge distribution. So next one, electric field at every point on the Gaussian surface must be symmetric. The angle between E bar and the area vector is so maybe 0 degree or 90. The 0 degree is 90 degree. So these are the applications of the Gauss's. So Gauss law is always applicable, but not always useful. So next one, so by using Gauss's law, so we can derive the expression for intensity of the electric field due to an infinity long uniformly charged wire. So this is also very, very important question. So 5 marks. Okay. So by using Gauss law, by using Gauss law. So derived an expression for intensity. So intensity of electric field, due to an infinitely long uniform charged wire. So this is very important question. Okay. So derive an expression for intensity of electric field due to infinitely long uniformly charged wire. So here now if you take the one wire, so this is infinitely long wire. Okay. So here by using the Gaussian, very important question. So here if you take the long wire, so this is the long wire. Okay. So here infinitely long wire. So this is infinity. Okay. So this is also infinity long wire. So let us consider a charge is distributed continuously along the length of the wire. So now we are going to now if we take the positive charge. Okay, so this is positive charge. Now use my charge in positive charge. Okay, charge. So let us consider an infinitely long uniform charged wire having the linear charge density. So why? Because charge per unit length of the wire is called the linear charge density. So in this wire having the linear charge density lambda. So lambda is equal to charge divided by length. So now if we take the infinity long straight wire, so this is uniformly charged. That means positive. So uniformly distributed along the length of the wire. Okay. So now by applying the Gauss's law or Gaussian Gauss's law. So here, so this is the center of the wire. So let P be a point. So let P be a point. Is that perpendicular distance smaller from the center of the wire. So let P be a point. Is that perpendicular distance smaller from the center of the wire? Oh. Okay. So this is really important. So let P be a point now. So now P and a point is one. So is that perpendicular distance. So here perpendicular distance smaller from the center of the wire. Oh. Center of the wire. So this is OP is equal to R bar. So this is equal to radial vector. So OP is equal to R bar. So this is the position vector or radius vector. So OP is equal to R bar is called the radial vector or radius vector. So now applying the Gauss's law. So we are already discussed. Now Gauss law apply compulsory. We can draw the Gaussian surface around the charge distribution. So now if we take the wire, so we can draw the cylindrical Gaussian surface around the charge distribution of the wire. So here let E is the intensity of the electric field at point P. So then now P and a point at intensity of the electric field find out. So E is the intensity of the electric field at point P. So first of all, we can draw an imaginary Gaussian surface. So here OP is equal to R bar is equal to radial vector. So now we can draw an imaginary Gaussian surface. So like this. So this is the cylindrical Gaussian surface around the charge distribution of the wire. So around the charge distribution of the wire. So like this. This is the cylindrical Gaussian surface. So here cylindrical Gaussian surface. So now we can draw an imaginary closed surface around the charge distribution of the body. So this is called the Gaussian surface. So this is the Gaussian surface. Okay. So here, so now if we take the center, so center of the wire to, so P point. So here P is the point. So it is at a distance small. So at point P, electric field is E. So this is positive charge and electric field is away from the positive charge. So now negatively charged and we use ಮಾಡಿದ್ರೆ electric field is towards the charge. Okay. So ಈಗ ನಾವು positive charge ಅನ್ನು use ಮಾಡಿದಕ್ಕೋಸ್ಕರ electric field is always radially outwards at everywhere. So here electric field is away from the charge. So here now point ಇಲ್ಲಿ ತಗೊಳ್ಳಿ. So electric field away from the charge. So here electric field is always away from the charge because of I am using the positively charged infinitely long straight line. So this charge is uniformly distributed. So now we can draw the Gaussian surface around the charge distribution. Okay. So here to find out the intensity of the electric field. So now, so in this Gaussian surface, so having the three surfaces. So this is a end face only. So this is end face. So this is end face 1. Okay. So this is end face 2. So next this is. So this is cylindrical surface or curved surface. So like this. This is a cylindrical surface or curved surface. Cylindrical surface 3. Okay. So here let so pi is the electric flux. Electric flux passing through Gaussian surface. Gaussian surface. So we know that what is the statement of Gauss law? The total electric flux passing through any closed surface, that means 3D surface, enclosing charge is equal to 1 by epsilon naught times the charge is enclosed. So here pi is the electric flux passing through a Gaussian. Here pi is equal to electric flux passing through end face 1. Okay. So electric flux through end face 1. So end face 1 plus electric flux through end face 2. So end face 2 plus electric flux through cylindrical surface 3. Okay. So electric flux through cylindrical surface 3. Okay. So now calculate these three surfaces. So that is the total flux. So pi is equal to electric flux passing through Gaussian surface. So now we can draw the Gaussian surface around the charge distribution. So pi is the electric flux through. So this is the end face 1. So this is the end face 2. So next if we take the curved surface or cylindrical surface, that is 3. So electric field is radial or everywhere. If we take any point on the Gaussian surface, electric field must be symmetric. So that is away from the charge. Because of now if we take the positive charge. So in case of negative charge, we can use electric field is towards the charge. Okay. So for example, so if we take the small element of area, so this is the small element of area of the Gaussian surface. So this is ds. Okay. So now already 3D surface. This is 3D surface. So 3D surface ಮೇಲೆ area vector is always outward normal is considered. So only outward normal considered as a 3D-dimensional surface, that is closed surface. 3D surface means closed surface. So we are already discussing in previous video. Okay. So here ds is also outward normal. So in this direction. So ds and e are in same direction. So what is the angle? So theta is equal to 0. So theta is equal to 0. So now, so this is the surface. So E surface ಮೇಲೆ now if we take the small element of area, so this is the ds. Okay, so E point of the intensity of the electric field is radially outwards, so this is E. So this is the small element of area ds, so this is outward normal, so here angle is theta equal to 90 degree. So E end surface ಮೇಲೆ electric field and small element of area is perpendicular to each other. So E Gaussian surface, that means the curved surface where electric field and ds are in same direction. So now if we take the end phase 2, so if we take the small element of area in this surface, so this is ds. So electric field is radially outwards. So that means already discussed. So electric field is symmetric, that means equal, constant, same at every point on the Gaussian surface. So this is radially outward because of now if we take the positive charge. So here ds is away from the charge. So here angle theta is equal to 90. So now E surface ಮೇಲೆ use ಮಾಡಿದ್ದು center of the wire tube. So this is point P is at distance smaller. So electric field is E radially outwards. So if we take the ds, so ds and E are in same direction, theta equal to so 0 degree. So this is very important. So E cylindrical surface ಮೇಲೆ E and ds are in same direction. So what is the angle theta equal to 0 degree? So end phase 1, E and ds element are in perpendicular to each other. So end phase 2, so E and ds are in perpendicular to each other. Okay, so what is the angle theta equal to 0 degree? So now applying the so electric flux phi is equal to closed integral. So end phase 1, so E bar dot ds plus closed integral end phase 2 E bar dot ds vector plus closed integral cylindrical phase E bar dot ds. So electric flux through end phase 1, so closed integral E bar dot ds, electric flux through end phase 2 plus electric flux through cylindrical surface. Okay, so here so pi E is equal to closed integral E bar dot ds, a dot b can be written as ab cos. So E ds cos theta. So here end phase 1, so E and ds are in perpendicular to each other. So E ds cos 90 degree. E ds cos 90 degree. So next plus, so closed integral end phase 2. So end phase 2 same, E and ds are in perpendicular to each other. So therefore E ds cos 90 degree. Plus if we take the cylindrical surface, in the cylindrical surface E and ds are in same direction. So therefore closed integral E ds cos 0. E ds cos 0. This is very important. So end phase ಮೇಲೆ second end phase ಮೇಲೆ E and ds are in perpendicular to each other. So what is the angle theta equal to 90? So is cylindrical surface or curved surface may fit at any point on the Gaussian surface, E and ds are parallel to each other. That means theta equal to 0. So cos 90 degree value is 0. So here also cos 90 degree value 0. So this factor is 0. Okay. So here second factor is also 0. So now only one factor is there. So that is closed integral E ds cos 0, cos 0 1. So E is constant. So now already so E is same at every point on the Gaussian surface. So therefore pi is equal to E common ಮಾಡಿದ್ರೆ so closed integral ds. Closed integral ds. So now if we take this, so this is the cylindrical surface. So here L is the length of the cylindrical surface. So this cylindrical Gaussian surface length value is to L. So here L is the length of the cylindrical Gaussian surface. So closed integral ds. So here ds means total area of the cylindrical Gaussian surface. So ds means the small element of area. So closed integral. So that means ds now all add ಮಾಡಿದ್ರೆ total area of the cylindrical Gaussian surface equal. Okay. So E into closed integral ds. So this is equal to area of the cylindrical surface. So that is equal to pi is equal to E into 2 pi r. So 2 pi r L is the area of the cylindrical surface. So that is the formula for area of the cylinder. So what is the formula for area of the cylinder? 2 pi r into L. So 2 pi r into L is the formula for area of the cylinder. So this is the equation 1. Okay, this is the equation 1. So pi is equal to E into 2 pi r into L. So now if you use the mathematical form of Gauss law. So now if you take the Gauss law, so we know that. So what is the formula for Gauss law? Closed integral E bar dot ds is equal to q by epsilon naught. So inside. So inside. So here closed integral E bar dot ds is equal to. So that means this is the value of closed integral E bar dot ds, that is pi e. So pi e is equal to what is the value? E into 2 pi r into L. So that is equal to Q inside divided by epsilon naught. Q inside divided by epsilon naught. So here this is the L is the length of the cylindrical Gaussian surface. So but it is infinitely long straight wire. But if we take L is the length of the cylindrical Gaussian surface, inside charge is Q. So what is the formula for lambda? Lambda is equal to charge divided by length. So charge per unit length, this is called the linear charge density. So by using this formula, Q is equal to lambda into L. So now substitute in this equation, E into 2 pi r into L is equal to lambda L divided by epsilon naught. So in both sides L cancel. So therefore E is equal to lambda divided by 2 pi epsilon naught into R. So this is the formula for intensity of the electric field due to an infinitely long uniform charge wire. Okay. So E is equal to lambda divided by 2 pi epsilon naught into R. So E is equal to lambda divided by 2 pi epsilon naught into R. So lambda is positive. So here positively charged wire. So lambda can be taken as negative. So negatively charged wire. So in what direction represents the electric field? So electric field is in the direction of the. So is in the direction of the away from the charge. So because of now, if we take the positive charge, what is the direction of the electric field? It is away from the positive charge. Now if we take the negative charge wire, electric field is towards the charge. So here lambda 2 pi epsilon naught is constant. So therefore E is inversely proportional to R. So E is inversely proportional to R. So here this R is increases. So this distance between wire to point P is increases. Electric field is decreases. Electric field is decreases. So in what direction represents the intensity of the electric field? It is directed away from the charge. So why? Because now we take the positive charge. So now negative charge can be used what the electric field is towards the charge. So this is the very important formula for intensity of the electric field due to an infinitely long uniformly charged wire. This is also one of the very important question in 5 marks. Okay. So in next class we are going to discuss another questions. Thank you.